How do we break down massive looking circuits into something actually solvable? And what changes when resistors are placed side by side compared to end to end? This is the foundation of all of circuit solving. Once you master this, complex diagrams start to melt down into simple equations. There's going to be a lot of new stuff, a lot of formulas and problems in this video. So if you haven't already, get the free cheat sheet in the description for this topic. So here's the first core idea. What does in series mean? Resistors are in series when they are connected end to end, and the current must pass through each of them one by one in that order with no branching. This is like having one narrow road that cars must follow one at a time. And here are some properties of series circuits. 1. The same current flows through each resistor. 2. The voltage is split across each one. And 3. The total resistance adds up. And lastly, if you remove one component, so for example, if you looked at this circuit before, if the current is going this way and it has to go through each one by one, if you take one out, then the entire loop is broken, no current will flow. And since total resistance adds up, which was the third property I mentioned, then you can have a single equivalent resistor equal to all of the individual resistors added up. And it would look something like this. So let's say we have our circuit with this is our battery, and we have our 3 resistors up here, comes back around. You could instead clean this up by having just one equivalent resistor that's the sum of all of the individual ones. And it will look something like this, much more clean. Every complex problem we will solve will use this idea. Let's go through an example problem. And we have to derive the total resistance in series. Let's start by applying Ohm's law, which is voltage equals current times resistance. And every single formula we'll use for all of the problems in the video today will be on the free cheat sheet in the description. If the resistors are in series, that means the same current I flows through each one of them. And the total voltage is the sum of the individual voltages, because like I said, the voltages get split up between each of the things when it's in series. The total voltage will be all of the individual voltages represented in the equation this. For Ohm's law, each resistor, because voltage is equal to current times resistance, each of these have current and the resistance. You have one for all 3 of these that we've written out like that. So that means you can factor out I, because I, the current, is constant for all of it. Yet total voltage equals I bracket all of the resistances added up. And this is equal to Req, which is what we were looking at before, the one equivalent resistor that replaces the need for all of these tiny ones. And we've now collapsed a 3 resistor loop into one. This is the math behind it. How about parallel? What does in parallel mean? Resistors are in parallel when they are connected across the same 2 points, creating branches where current can split. Imagine this like multiple water slides that start from the same height. The water, which is the current, can pick which slide it wants to go down, and each slide will still see the same pressure or voltage at the very top. The properties of parallel circuits are this. 1. Voltage across each resistor would be the same instead of split like it is in series. 2. The current splits between branches. And 3. The total resistance, so the overall resistance added up, is less than any single resistor. I'll say this again. The total resistance is less than any single resistor. 4. If you remove one resistor, unlike series circuits, current can still flow through the others, so it doesn't break down. So I'll show you some examples. This would be a parallel circuit. Let's say we have point A, and it branches off like this, where the current can split. We have one path up here with a resistor leading to point B. We have one in the middle, with one down here. Let's say our battery is here. R1, R2, R3. Voltage, current flowing this way. This is parallel. And the equivalent resistor, instead of adding up all of these, you add it up like this. 1 over the equivalent resistor equal to 1 over all of the individual resistors, and you add them up. Very similar thing. This is parallel. The resistors share the same top and bottom points, and each resistor sees the same voltage. So you can see this is a branching layout. All resistors share the same end and start points A and B, or top and bottom. Let me show you another diagram we could draw. Let's say this is our battery. I'm going to wire some light bulbs up in parallel. This is our bulb, another bulb, another bulb. Parallel would look like this. You get the voltage from the same battery, but it's all separate. Series would look something like this, right? By one battery, and then it all just goes here. One by one, the current flows through, And if you take one out, it breaks. If you take one out here, the current can still flow through to the other ones. And each of our lights sees the same voltage. And if we wanted to replace it all with one equivalent resistor, it's the same thing. It would look like this. Just like the series example I showed you. Let's do some math here. We're going to derive the total resistance in parallel. And each branch of something in parallel gets the exact same voltage V. It's not split between them like it is in series. So using Ohm's law, we see I1 equals V over I1. So the current flowing through the first point and the resistor at the first point, but the voltage is constant this time instead of current. And do this for 2 or 3 as well. And I'll quickly write that out for you. This means that the total amount of current leaving the battery is equal to all of the individual currents added up, which is equal to all of the individual VRs added up. There. And this equation here, the total current is equal to all of the currents added up. We can write it like this. Since V is constant, we can factor it out. I equals V times 1, all of the resistors, and all of these resistors added up is 1 over the equivalent resistor. And there we go. Total resistance is equal to all of those. So the more paths that your current can take, the easier it's going to flow. So the total resistance goes down. Here's a conceptual example. You have 2 configurations. So here's a battery. Here's 2 light bulbs. It's got positive and negative at 12 volts. It links up like this. This is series. How about the second one? This one will be in parallel, providing the same voltage. However, since it's parallel, the setup is different. It's going to connect up like this. It's not in series. Which one of these is going to make our light bulbs brighter? This is going to put all of that mathy stuff into practice. In parallel, there's more current that gets drawn overall. And since power is given with current times voltage, since voltage is the same in both setups, the variable is current. And since current is higher in parallel, the total power is higher, which means parallel circuit will give you brighter light bulbs, even with the same voltage and the same amount of light bulbs. What have I drawn here? I've quickly drawn a simple circuit. You have 2 resistors that are in parallel, because remember the zigzags are resistors, and it's connected to a laptop charger here, running at 36 volts. Your laptop is drawing power from this charger. One branch powers the screen, say this one, which is 140 ohms. And the other branch powers the keyboard LEDs with a resistor with 210 ohms of strength. How much current goes through each branch? So this would be I1, this would be I2. And what's the total resistance of the setup? Here's what we're given. We're given the value of R1, R2, and the voltage. Each branch, since it's parallel, gets the full voltage supply of 36V. So we can calculate the current in each branch. I1, current, Ohm's law is given with voltage over resistance. The voltage being constant, 36. The only thing that changes is resistance, which for I1, it's 140 ohms. This will power our screen with 0.257 amps of current. How much current goes into the second branch? We do the exact same thing. The voltage over the resistance, which is 210. And the voltage is 36. The answer for the I2 value is 0.171 amps flowing through here. The total current being drawn from this charger is 0.428 amps, which is simply these 2 values added up. And it gets split between here, as you can see. How about the total resistance if we wanted one equivalent resistor? This total resistance is given with V over I, which is what we were looking at earlier. 36 over the total current, which we just found 0.428, which is roughly 84.1 ohms. What does that number mean? It's not 140 plus 210. What it's saying is this combo of resistors acts like a single 84 ohm resistor with 0.428 amps of current flowing through it. That's what it tells us. What we've done is we analyzed what we knew and what we're looking for, and this formula involves total current, which means we have to find the individual currents to add them up. The free cheat sheet in the description makes this much easier because you don't have to flip through your notes to find the formulas that you want. Let's go through another problem. Let's have the same 2 resistors, but this time we're going to connect them in series instead of parallel. So we have the same charger, 36 volts, same R1 and R2 with the same resistance strength, and the total resistance, if you just add them straight up, 140 plus 210, giving us 350 resistance. What if we want to find the current? Current is given with voltage over resistance. This is the total resistance. So not the equivalent resistance, it's just the straight up total resistance that our current, let's say it's flowing this way, it's going to have to go through these both one by one. So 36 volts, and then it has to hit 140 plus 210 resistance as it flows through, which is this number, 350 ohms. The answer is roughly 0.103 amps of current flowing through. How about the voltage drop across each resistor? Because in parallel, each thing gets the same voltage. What changes is the current. In series, the current is constant. It's the same amount of current flowing through, but the voltage is split between each thing. So the voltage at this point would be the current times the resistance. And this is Ohm's law. This is 0.103, which is our current, times the resistance, which is 140, which is 14.4 volts at this point. How about for the second one? It's the same thing. The current, 0.103, times the resistance, but this time it's 210, giving us 21.6 volts. The total voltage, if you notice, these individual voltages, adds up to 36 volts, which is our total voltage coming in. That's how it gets split between the both. So the current flowing through is the same. The voltage is shared between them, adding up to our total voltage coming in from our laptop charger. Here's another example problem, and this one will be the last one that we go through today. Sorry, this might have scared you. I've drawn a giant diagram here. This is the next problem we're going to solve, and it's a series circuit plus a parallel circuit. It's a combination of the two, and this is what we're going to solve for. 1, the total amount of current that gets drawn from this battery supplying 12 voltage, and 2, the voltage across this parallel section, and 3, the amount of current through each parallel resistor. Let's start with making some space. This is the kind of diagram you're going to be seeing a lot in this topic. So finding things like the current is going to need our equivalent resistances. So let's start with this parallel block. If you remember, and this is on the free cheat sheet, the equivalent resistance is not all of them just straight up added up. That's how it is in series. In parallel, it would be the strength of a resistor that could replace these two. In parallel, it's 1 over. So let's label it RP for parallel. This is 1 over the first resistance, 320, plus the second resistance, 480. When you add this as a fraction, you have 5 over 960. So you can flip it, get RP equals 960 over 5, giving us 192 ohms as the equivalent resistance for the parallel block. For the overall total equivalent resistance, we have to add in our series one as well. So simply 220 plus 192, which is 412 ohms in total. That is the equivalent resistance for our whole circuit. The total current from the battery we can now find because we know this. The current given with Ohm's law is V over R. Voltage is 12, resistance 412 is roughly 0.0291 amps, or in milliamps, 29.1. That's the total current that gets drawn from this battery. It flows through this 220 ohm resistor first. How about the voltage across the parallel section? We'll label it VP. It's equal to the current, which we just found, 29.1 milliamps, multiplied by the first resistor, which is the series one in 220, which is 0.0291 times 220 equals 6.4 volts. So the remaining 6.4 volts is what is dropped across these parallel resistors. This is labeled as I1 and I2, so that's what we're going to say. Honestly, that's a bit of a mistake on my part because I should have labeled them 2 and 3 since these are the second and third resistors that our current goes through. This is the true I1, but that's arbitrary. For I1, which is our 320 resistor, current's given as voltage over resistance, which is 6.4, because that's how much voltage is left over after it crosses through the 220 resistor at the start, divided by the resistance 320, which is 20 milliamps for this top branch. How about for this bottom branch? It's the same thing. 6.4 volts over 480 resistance, giving us 13.3 milliamps. These add up, so I1 plus I2 would be 33.3 milliamps. This is proof that there's some rounding error somewhere here because of decimal approximation, because the total overall is meant to be 29.1. If we used unrounded values from when we found the total current, it would match up. It's just a decimal approximation thing. Our solving approach was correct.